and the sieve tube member, or the albuminous cell and the sieve element in gymnosperm. Those arise from the same mother cell. So in the development of the phloem, when that last cell division happens, and one of these cells is going to be a sieve element, the other one will be a companion cell associated with that particular sieve element. They come from the same original cell. Companion cells alive contain nuclei, abundant organelles, mitochondria, ribosomes, membrane system, the endoplasmic reticulum, all the parts of the normal cell that you think of. Those are found in the companion cell, not in the sieve cell. And it's thought that you know, the ability of the sieve cell to be alive is because it's associated with a companion cell right next to it that's providing a lot of the function that the sieve cell would normally have to do by itself. There's lots of plasmodesmatal connections between a companion cell and the adjacent sieve cell. So where do we go? Here's a companion cell, here's a sieve tube member, and there are lots of plasmodesmatal connections between these two cells, lots of them, which indicates that there's a lot of things moving one way or the other between those two cells. A lot of solutes, most likely. And we'll get into that. Companion cells are thought, well, you can erase this are thought. Companion cells play a major role in the process of phloem loading. How does photosynthate get from a mesophyll cell into the phloem? Okay, so the end product of photosynthesis typically is sucrose produced in the cytoplasm of the photosynthesizing cell. That sucrose in the cytoplasm of that cell has to get into the phloem, into the sieve tube. How does it do it? What's the pathway that it takes? Companion cells have a big role to play in that transport process. And I'll talk about that next week. Here's some more images. All right. Okay. So here's a sieve tube. Here's a sieve tube member. Here's a companion cell. Here's a sieve tube member. Here's a companion cell. Looking on a cross section. Here's a sieve tube cell. Here's a companion cell. Here's a companion cell. Here's a companion cell. You see, they're right next to each other. Here's another line drawing showing a sieve tube member and a companion cell right next to it. Another cross section. Here's a sieve tube member with a companion cell next to it. Here's another one, another companion cell right there.
The companion cells are connected to each other by the plasmodesmata, or not really?
I think typically not, but they are connected to other cells that are adjacent to it. But I don't think necessarily another companion cell, no. But any mesophyll cells, like, I don't know what this cell is, but maybe this one. You know. And sometimes there are lots of plasmodesmatal connections. Sometimes there aren't, depending on different species and things. And that has to do with this pathway of loading solutes into the phloem. So different plants do it. Sure.
So you're kind of getting at this, but do companion cells only serve one sieve tube member?
Yes, yes, I think so. Yeah. It's a one-to-one correspondence. Yeah.
I just didn't know, because that one,
yeah.
that line drawing, if there's sandwiched between two. So
yeah, I mean, this is, who knows what this really looks like. So yeah. It's just a drawing, but yeah, I think there's a one-to-one correspondence because they arise from the same mother cell. So yeah, and that's why I don't think there are connections between companion cells and other companion cells. But there may be between mesophyll cells adjacent to the companion cell. Okay. All right. The other constituents in the phloem, fibers, right? These provide structural support. They're also dead. They have thick, highly lignified cell walls. They're strong. They just provide some support to the whole vascular system. Sclerenchyma. So sometimes this is the sclerenchyma cells are the same as fibers. Sclerenchymatous cells, right? Say that. And then parenchyma, that's the other kind of cell. Sclerenchyma and parenchyma. So the parenchymal cells are cells, just like in the xylem, there were parenchymal cells associated with the xylem vessels. There are parenchymal cells associated with the sieve tubes in the phloem system. And these also may play a role in lateral transport of substances into or out of the phloem, or storage of substances, or at least some of these parenchymal cells retain the ability to differentiate into other vascular system constituents if need be. So if the vascular system gets damaged and the plant has to try to repair that damage, some of these parenchymal cells may be able to differentiate into, say, a new little xylem vessel or a new part of the phloem or something. But really, it's hard to, it must be hard to work with these cells because there's not a lot that's, that you can find that's definitively stated about these things. So these do this, that, or that. But they're part of the vascular system. Phloem sap, so the stuff in the phloem. Unlike the xylem, where it's a dilute solution, but there are things dissolved in the xylem, like those ionic solutes that increase the hydraulic conductivity of the xylem. There are things dissolved in the xylem, but not much, especially compared to the phloem. The phloem tends to be a relatively concentrated solution. So what does that mean? That means the osmotic potential in the xylem is close to zero. But the osmotic potential in the phloem is usually quite negative because it's a concentrated solution. Remember this CRT, right? So phloem has high concentration. Xylem has low concentration. So the osmotic potential in the xylem close to zero, osmotic potential in the phloem quite negative. Most plants, the solutes that are found in the phloem are carbohydrates, and most commonly sucrose. Remember, sucrose is the end product of photosynthesis, right? What are the three parts of photosynthesis? Do you all remember? The light reaction, the dark reactions, or the Calvin cycle, and sucrose synthesis. That's the third part. So sucrose is a photoassimilant, right? That's a product of photosynthesis. And in most plants, that sucrose somehow finds its way into the phloem. Other plants use more complex carbohydrates, but coming from the same source. Other more complex like stachyose, rhabascose, raffinose, which are just bigger and bigger sugars, but same, so ultimately the same origin in photosynthesis. What else is found in the phloem sap? Various amino acids, inorganic cations, potassium, calcium, anions, you see some here, and things like ATP, hormones like IAA and ABA, right? The indole acetic acid and auxin, and ABA, abscisic acid, which has a big role to play in root to shoot communication. The pH in the phloem is typically above 7. It's a bit alkaline compared to the xylem, where the pH is a bit acidic, pH of 6. In the xylem would be typical, in the phloem, neutral to a little bit alkaline. Now, the phloem is the system that the plant uses to move those photoassimilates from sources to sinks, from sites of production to sites of utilization of those photoassimilates. And so, if you look at the phloem system, you see sucrose moving from high concentration, the source, to low concentration, the sink. So here we have a transport from high concentration to low concentration, but diffusion is not the process that's driving that. In the phloem, just like in the xylem, the driving force for the movement of the fluid is a gradient in pressure potential. It's a difference in pressure, convective transport that moves the stuff in the phloem, just like in the xylem. So we can use, as a first approximation, this Hagen-Poiseuille, right? In the phloem, just like in the xylem, the driving force is this difference in pressures, the gradient in the pressure potential that's making the stuff move. The flow caused by this difference in pressures, and then you got some terms in there, you know, that determine the conductivity of the pathway. All right. Now, unlike the xylem, though, the phloem, the transport system of the phloem, is surrounded by a membrane. Right? But once you're in the sieve tube, no membrane. And so we have this controller. But to get into the sieve tube, that's where you have to cross a membrane. And that has some important implications and differences between the xylem and the phloem. Okay, so within the phloem, mass flow is what's driving convective flow in response to different temperatures, just like in the xylem. And it happens to be that this flow in the phloem, flow transports whatever's dissolved in that fluid from high pressure to low pressure. And that's typically from a source, like a leaf, to a sink, like a growing root. The sucrose will be transported that way from high sucrose concentration to low sucrose concentration. But it's the pressure difference that's causing that fluid to move, not the concentration of sucrose. All right. How fast can things move? 0.3 to 1.5 meters per hour in the phloem, which is slower than in the xylem. Remember, in the xylem, I put this here because I don't remember, but in the xylem it was about 3 or 4 meters per hour. In the phloem, it's maybe 1.5 meters per hour. So things move slower in the phloem than in the xylem. The fluid moves slower in the phloem than the xylem. And within the, talking about the phloem, a lot of times we're not worried about how fast can something move, but how much of the stuff moves, how much sucrose is transported from here to there. And to get at that question, we need to know what the concentration of sucrose is. If we assume 500 moles per cubic meter, which is not an unreasonable value, that may be typical, you can calculate a transport rate of around 300 moles of sucrose per meter squared per hour. That's per meter squared of open sieve tube. So that's a big number. But this is per meter squared of sieve tube lumens. And if you just look at the sieve elements themselves, maybe 10 grams per centimeter squared of the sieve tube element per hour. So not a super high rate, but an efficient way to transport sucrose around the plant. And remember, there's, in the vascular system, in the xylem and the phloem, there are a lot of redundancies. There are a lot of parallel pathways. There are a lot of phloem, a lot of sieve tubes within a stem of a plant, and a lot of xylem vessels within the stem of a plant. There's a lot of redundancy in that system, so you get parallel transport pathways, which can be quite efficient at transporting water and sucrose. Right? Do you remember all this from review? If you do, you're better than me, because I don't when I took like this. Sure.
So on the concentrations, high concentrations for the phloem, low concentrations for the xylem.
Right.
There must be a kind of a big implication coming based on the size of each of them, right? Like xylem size is greater than phloem size. Then there is less space and the stuff is more concentrated.
Yeah, but also remember, the phloem is the system that the plant uses mainly to transport sucrose or other photostimulants. The xylem is the system that the plant uses to supply water for transpiration. And so the size difference between phloem and xylem, I don't think is so much due to because difference in solutes, but to their function. So there's a lot more fluid moving through the xylem than through the phloem in any plant, typically. If it's a sunny day and the plant is okay. There's a lot more fluid going through the xylem. The vessels are a lot bigger, and so in the xylem, you need a smaller gradient in pressure to move a lot of water because the vessels tend to be big. Compared to the phloem, smaller, then you need a bigger gradient in pressure to move the same amount of fluid. Or conversely, for the same gradient, you get less flow through the phloem than you do through the xylem. Yeah. And that has to do with, balancing transpiration rates and rates of movement of sucrose to do whatever the plant has to do, to grow the roots, to store in an organ like a potato or a carrot or something. Yeah. And so it's just, it's a balancing act, and different plants. These are generalizations, that the xylem typically much bigger vessels than the phloem. I hesitate. I'd say almost all plants, because I'm not sure it's all. But and that has to do, I think, because a lot more fluid is moved for transpiration than for getting sucrose where it needs to go. So one of the ways, this is an interesting thing. One of the ways, how do you study flow? How do you study movement in the flow? How do you study what's in the flow?
So, one question. I get it why the xylem move the stuff up because of the different potentials, because of the atmosphere. But how does the flow? It's opposite. What's in the roots that's
very good question. Very, very good question. Yeah, I will answer that question, but maybe not right now. But yeah. That's where we'll go. I will answer that question. That's very, very good question. Actually, turns out it's a circulatory system. Water is moved up the xylem, and then once it gets into a leaf, and always remember, xylem and phloem are close to each other. So water moves from the root system up to the leaf in the xylem. Most of that water goes for transpiration, evaporates and goes out into the atmosphere. But a little bit of it moves from the xylem into the phloem that's right adjacent to it in the leaf. So you have water moving up from the below ground to the leaf, a little bit of water moving into the phloem. Then the phloem moves from here down to there. When it gets down into the roots or below ground, some of that water in the phloem moves into the xylem. And you get a circulation then of water in that vascular system between the xylem and phloem. Now, why does the water move one way at the top and the other way at the bottom? It's because you're crossing a membrane, and they're difference in solute concentrations and pressure, solute concentrations, solute potentials. osmotic potentials and pressure potentials cause a difference in the total water potential in the leaf. Remember we have this, this is for a tube, and for the membrane, we have this flux, what delta psi, plus difference in the total water potential, if this is one, right? So in the leaf, the total potentials in the xylem and the phloem are such that water moves across the membrane that surrounds the phloem from the xylem into those sieve tubes. Because the total water potential is more negative in the sieve tube up at the top of the plant than it is in the xylem. Down at the bottom, in the roots, the gradient's in the other direction. The xylem has a lower total water potential than the phloem, and so the water moves across the membrane, out of the sieve tube, into the adjacent xylem vessel. So it moves one way at the top, other way at the bottom, and makes a circulation like that of water through the system. And it has to do with, there is a membrane there, and that's what causes these things to happen. So, very good question. I jumped ahead of myself. Right? I'm trying to keep it secret, but it's no secret. That's how it works. Yeah. So, and remember, the other part of to answer your question, the other part is the plant itself cannot control its pressure potential. It can't control this difference in pressures or this difference in total potential. It doesn't have control of it. The only thing it can control is osmotic potential through the production, making more solutes or fewer solutes and changing the concentration, changing the osmotic potentials. So that whole circulatory system, which is dependent on difference in total potential one way at the top and the other way at the bottom, is determined by the plant regulating the concentration of solutes in the system at those different points. And how it does is it puts solutes into the phloem at the source end, and it withdraws solutes from the phloem at the same time, changing the osmotic potential, which changes the total potential, which sets up these gradients, which makes the circulation happen. That's in a nutshell the answer to your question.
Thanks.
But I'll don't worry, I'll expound on that next week. Very good question. So how do you know what the pressure potential is in the phloem? We're getting back to this one. How do we know what the pressure potential, how do we know what the constituents are in the phloem? After all, remember that guy Dixon, when he had invented the pressure chamber, was cutting off plants and pressurizing them and trying to get stuff to squeeze out of the inside of the plant. Well, that was mostly coming from the xylem, because the phloem system, very efficient at plugging itself up when it gets damaged. In almost all plants, if you damage the phloem, if you make a cut in it, if you sever it, if you poke a hole in it, it will plug itself up very quickly. There are exceptions. This plant's an exception. Ricinus, right? Castor oil, this plant, castor bean, poisonous, big seeds, big leaves, tall thing. This one doesn't plug up its phloem. And so this one's been used a lot for investigating what's in the phloem and doing experiments with phloem. But it's only one species. All the other species almost plug their phloem up very quickly. So how do you get in there to do things? Well, that's where we can rely on aphids. Aphids, right? They're little insects that feed on plants. What do they feed on? They feed on stuff in the phloem. Aphids have, a piercing, sucking mouth part. Remember entomology? Did everybody take entomology? Anybody? I took it, but yeah, piercing, sucking, right? It's Homoptera? Hemiptera? I always get them mixed up.
I don't want to get into something like that.
Yeah, me either. That's why I don't have it on the slide.
I can look up right quick.
No, I mean, it doesn't matter, whatever they're called.
You mean not-
But the thing that matters is the mouth part of the aphid is like a hypodermic needle, right? It's a hollow tube. And what happens is the aphid feeds by sticking its stylet, its hollow tube, into the phloem of a plant. And once it gets it in there, then, you know, it just sits there and whatever's in the fluid, whatever's in the phloem's going into the aphid. And you know, it provides a pathway through it for a fluid to go, and it takes out what it wants, and that's how it lives.
It was Hemiptera.
Hemiptera.
It's a true insect or a true bug.
Oh, a true bug. Okay. Okay. Good. Well, the good thing about them is, what people have done is to allow the aphid to feed on the phloem, to get started feeding on the phloem, and then come along and cut the aphid off of its stylet, right? Get rid of the aphid. And that, now you've got a little tube right into the phloem. And it can sit there and it won't plug up because the aphid's got some, you know, whatever it's got that the plant is not going to plug it up. Yeah, it's got enzymes or whatever, I don't know what it is. But it provides opening right into the phloem. And you cut the aphid off, and then you can collect whatever comes out that little tube. In fact, you can put a manometer on it and measure the pressure that's inside the phloem. Yeah,
That
can you
big?
believe it? Yeah, that's a little tiny thing. Yeah, so you can measure pressure potential that way. And the aphids have been used a lot for just this purpose. Otherwise, how do you do it? They're very efficient at finding where the phloem is from the outside of the plant. You know, they can find it and put their mouth part right in there. You know, I mean, you try to do this under a microscope or something, how do you even do it? You couldn't do it, right? But the aphid's smarter. It knows how to do it. Then we cut its body and play around with what's left. So, aphids have been used as a system to investigate the stuff in the phloem, and that experiments like this have been used to confirm this idea of the circulation of fluid between the phloem and the xylem in the vascular system of the plants. And I'll have a little bit more to say about that next week. Sure.
I have a question. It may look like kind of time question, but after they cut off the thing, I was gonna feed out itself later.
How does what?
The insect gonna feed out itself later, so
No, the insect, you get rid of the insect. You throw it in the garbage can.
Oh.
It's died. You don't need the aphid anymore. No. You get rid of the aphid. All you need is its mouth part, right? Because it's a tube. That's all I care about. Throw the aphid away. And then you have your little tube, and you can do an experiment. You know, yeah, I know it's cruel, but it's just an aphid. There's many aphids around. There's plenty of aphids. Do not have to worry about them. Okay, maybe the entomologist would say, oh, poor aphid, but you know, we don't have to worry about that. Okay, so next time what I want to do is talk about, expand a little bit more on this transport system within the phloem and the xylem, and talk about phloem loading, unloading. I'll do that next week. So have a good weekend and see you later.